These will be these 3 lectures will be on sort of basic features of ADS-CFT. And if you are bored, you can leave. If you are interested in reading more, though, if you're not bored at all, you're confused, you can Google me, and you'll find that on my website I have a long series of lecture notes on ADS-CFT. This is sort of a very condensed, hopefully a bit speeded up version of those lecture notes, but you can go ahead and read online. So what is ADS-CFT? Well, ADS-CFT from my point of view is the statement that ADS quantum gravity is the same thing as a CFT. Hopefully from the earlier lectures of this course or your own prior experience, you know something, maybe a lot, about what conformal field theories are. So a lot of these lectures are going to be about how everything that you know about conformal field theory has some ADS analog that's relatively simple to understand. Now, ADS-CFT is a really big deal. There are 2 reasons that are a priori rather different why you might care about ADS-CFT, 2 among many. One is that we generally have great difficulty even defining quantum gravity in a non-perturbative way. And ADS-CFT provides both a definition of quantum gravity and an exact description of it. So a reason you might care is non-perturbative quantum gravity. So that's one reason why I care. It's a reason why you might care. But another reason, which is more closely related to the Bootstrap, is that ADS-CFT really provides us with a new kind of perturbation theory. So we're all hopefully very familiar with the fact that you can study weakly coupled fields in d dimensions and derive all kinds of interesting quantum field theoretic predictions. But that kind of Lagrangian description doesn't always get you to interesting, strongly coupled theories. ADS-CFT, and in particular just studying quantum field theories or string theories or general relativity, basically any kind of theory you want to throw into this ADS box, gives you a way of doing perturbation theory, starting not with sort of the approximation of weakly coupled particles in d dimensions. So this is going to be d-dimensional, and this is d plus 1-dimensional. But basically starting with a generalized free CFT or Gaussian correlations, and then perturbing around that by adding some small corrections. So in particular, we get a new kind of perturbation theory, which allows us to solve many theories and limits that we didn't have access to before. And in particular, for the purposes of this workshop, we get infinitely many solutions of the Bootstrap equation. So in other words, if we have a well-defined quantum system in anti-de Sitter space, like just an ordinary quantum field theory or a quantum field theory coupled to gravity, then via the ADS-CFT correspondence, we can generate crossing symmetric conformal correlation functions. And if our theory in ADS is unitary, or at least unitary to the approximation at which we're working, then we'll get fully unitary positive solutions to the crossing equation. So this is a good thing to know about. Even if you don't care about quantum gravity, you're a hardcore field theorist, you don't want to study black holes, whatever. If you just care about field theory, this is a good thing to know about, because if you're studying the Bootstrap, you can't rule out solutions that can exist, and this provides you with a way of generating a huge class of solutions. OK, so that's all the philosophy. Now we're just going to start talking about what ADS is and eventually how it relates to conformal field theory. So Euclidean ADS is perhaps best viewed as the hyperboloid which is a solution to this equation for d plus 2 variables. It's a hyperboloid. Notice that on the right-hand side, I've written an r squared, which is just some fixed number. So this is r ADS. It's the ADS curvature scale. So it's something to keep in mind when you're studying ADS is that intrinsically there is a length scale. I will often, and we often set this r to 1, but that means we're measuring everything in units of the ADS curvature scale. So the reason why this presentation of ADS is so great is that it makes the symmetries of ADS very, very manifest. In particular, the ADS isometries are just the SO1, d plus 1 Lorentz transformations of this d plus 2 dimensional space. So in particular, you can just write out some Lorentz generators, LAB, which are XA d dxb minus xb dA. And those are all the isometries of the space. So of course, writing out coordinate systems and talking about all of the isometries in nitty-gritty detail is rather dry. So I'd recommend, if this is new to you, that you take this formula for the ADS isometries and work out what they actually correspond to in the various coordinate systems that we're about to write down. So this coordinate system, just using the x's, is perfectly fine. But conventionally, we use many other different kinds of coordinate systems for ADS. And they all come from facts that you learned in high school about various nice functions that satisfy that equation. So all of the common solutions, all the common coordinate systems that parameterize this hyperboloid correspond to such solutions. So you're probably familiar with cosh squared minus sinh squared is 1. 1 over cosine squared minus tangent squared is also 1. The square root of 1 plus r squared minus r squared is 1. And then there's a particularly fancy example, which is 1 half z plus 1 over z squared minus 1 half z minus 1 over z squared equals 1. So all of the ADS coordinate systems that I will now write down for you just choose different combinations of these simple functions to parameterize the x's and give you the ADS metric. And they have different benefits. They make different symmetries obvious. Some of them correspond more naturally to black hole metrics. So let's see 3 of the most common examples. So, yeah.
Is x not restricted to be positive, or because it's a disconnected space?
I will restrict x naught to, I'm not going to sort of worry about this for the point of view of this lecture, but let's say x naught is positive. So in the parameterization that we'll use for global coordinates, x naught is r cosh some sort of Euclidean time parameter tau over cosine of a sort of radial parameter, as we'll see in a second, rho. You can also parameterize this using this example as the square root of capital R squared plus little r squared cosh tau. Or you can parameterize it using our last example as 1 half z squared minus, plus r squared over z plus x vector squared. So that's for x naught. For x1, then we use sinh and the expected thing. So let me just quickly write that out for you. in this way. And then, sorry, this is d plus 1. This is just a convention. You could call it x1 if you like, but we conventionally call it xd plus 1. And then the other xi, where I runs from 1 to d, are either r tan rho times some angular direction, or r times some angular direction, or r over z xi. So what do these three different parameterizations give us for the metric? Just working this out using the fact that the x's, that the line element for the x's is dx naught squared minus dxi squared. We find three conventional metrics. One of them is 1 over cosine squared rho times d tau squared plus d rho squared plus sine squared rho d omega squared. So this is a d minus 1 sphere. This can also be written as capital R squared plus little r squared, because I'm keeping the ADS length scale, dr squared over little squared plus big R squared. And finally, one of the most common metrics, the Poincare patch metric, which takes this form. You mean, let's not keep capital R. So let's avoid confusing ourselves. Anyone else? Just set capital R equal to 1. Good. So these are three different metrics that you'll commonly encounter in the literature, and each one has its advantages. So for our purposes, we'll mostly think in terms of global coordinates. But this Poincare patch metric is also something you'll commonly encounter. So I told you that ADS isometries are really obvious in this presentation of ADS, Euclidean ADS. So there's still some isometry in global coordinates that remains obvious. Various different isometries remain obvious in these different metrics. But in global coordinates, there's a time translation symmetry in tau. So that is, it will turn out to be the dilatation operator, which is LD plus 1, or in terms of tau, it's just the operator d tau. And this is a particularly physically important symmetry generator. I'm sure you've heard of it earlier in these lectures. And notice that in this global coordinate system, the dilatation generator, the thing that I've called dilatations, is time translations. What that means is that the ADS Hamiltonian in global coordinates is the dilatation generator of the CFT. So that immediately implies that ADS energy in units where I've set r equal to 1 is identified with CFT dimension. So that will be important for any time we think about physics in a kind of qualitative way, because we'd like to understand sort of what the low dimension spectrum of the CFT is. That corresponds to low energy states in ADS. The high energy states correspond to the high dimension spectrum. Probably even encountered statements about how the conformal bootstrap converges very, very rapidly in dimension. That would correspond to the fact that it's only sensitive to the low energy states in ADS, et cetera. So this is an important concept to keep in mind. And if you've never done any of this before, you can check that this is the same thing as z dz plus x dx in the Poincare patch. So just using this identification. So what happens if we want to study Lorentzian physics. We actually want to not just study a Euclidean CFT, but we want to study Lorentzian ADS CFT. We want to study actual dynamics in anti-de Sitter space. Well, a convenient thing about global coordinates is that Lorentzian ADS just corresponds descending tau to IT. So that's it. These metrics become the Lorentzian ADS metric. And that completes the statement that this is really sort of the physical energy that you as a dynamical observer would measure. Now, what does this correspond to in this picture? Well, it just corresponds to the fact that Lorentzian ADS changes the signature in this way. So now we have a 2, D signature metric instead of a 1, D plus 1 signature metric. And you can check that all this, that just doing that takes us to a solution to this hyperboloid. Now, what about the Poincare patch? Well, the Poincare patch is a bit more complicated. Yeah. Yeah, I'm reinterpreting. I mean, this coordinate system is a solution to this set of equations, where I have sine t and.
Yeah. All I'm saying is that to go to what you just wrote now, you have to redefine x equals 1 compared to what was there.
Yeah. Yeah, you have to get rid of the I, sorry. Yeah, indeed. So you have to get rid of the I. And then you have this hyperboloid solution. OK, so the subtlety with regard to the Poincare patch, which I don't really want to spend a lot of time on because I'm mostly going to use global coordinates, is that in the Euclidean case, all of these different coordinate systems all cover the entirety of global ADS, including the Poincare patch coordinates. However, we have to do something slightly more complicated to identify the Poincare patch coordinates in the Lorentzian signature, and the Poincare patch no longer covers all of global ADS. It only covers a causal diamond. So I'm not going to use the Poincare patch coordinates. If you don't already know this statement and you'd like to see it, you can look up my lecture notes. But it's just something to be aware of if you're studying ADS CFT. OK, so now what's good about these 3 coordinate systems? So the thing that's good about the Poincare patch coordinate system is that if you want to study a CFT that's very obviously, manifestly living in flat space, then this is a nice coordinate system. It manifests Euclidean rotations and translations in xi. That's one thing that's nice about it. There are nice things about these 2 coordinate systems as well. One of them is kind of trivial, but nice to know. This coordinate system can be modified simply to obtain a black hole solution. So this is just a nice fact to know. You just said 1 plus r squared to 1 plus r squared minus mu over r to the d minus 2. And you obtain a spherically symmetric ADS Schwarzschild solution in d plus 1 space-time dimensions. So this is just a nice fact to know. But for our purposes, this coordinate system has a lot more information because with this coordinate system, it's easy to understand the causal structure of the space-time. So if you're familiar with Penrose diagrams, then you know that from this coordinate system, you can easily obtain a Penrose diagram for Lorentzian ADS. If you're not familiar with Penrose diagrams, the idea is that if you're only interested in the causal structure of the space-time, then you can perform some arbitrary Weyl transformation of the metric without changing the trajectories of light rays. So what does this coordinate system look like? Well, let's finally draw the ADS cylinder. We have the time t. We have a radial rho coordinate where this is rho equals 0, and this is rho equals pi over 2. And then we have some SD minus 1 sphere. So in this coordinate system, when we flipped to Lorentzian signature, we can immediately see what the trajectory of light rays is in this spacetime. In particular, light rays just take trajectories that are that move on 45-degree angles in this picture. So even though the Lorentzian ADS space is infinite, t is infinite in extent, and the spatial distance from rho equals 0 to rho equals infinity is also infinite. Sorry, rho equals pi over 2 is also infinite. We've compactified the space in our visual representation so that we can understand the physics. So another feature of this rho coordinate system we can see is that at a qualitative level, there is a blue shift as we drag some object out to larger and larger rho. The coefficient of dt squared increases as we take rho to be bigger and bigger. This effectively means that we need more and more energy to drag something out towards the boundary of ADS. So
if you start from some frequency, you would expect that it would lose energy.
It would lose energy, so it redshifts. Yeah, sorry. It's a redshift in the sense that yes, exactly. So there's a effective potential in ADS that pushes you towards the center. And we're going to see that in much more detail in just a second when we determine what the geodesics are in ADS. But this fact basically gives you some intuition that the ADS space acts like a box or like a cavity. Even though it's an infinitely big spacetime, finite energy states are mostly confined to some small region near the center. Great.
Very basic question.
Yeah.
What do we mean by center of a maximally symmetric space?
That's a very, very good question. So how could this space even have a center? Well, I'm going to define some particular choice of coordinate system and some choice of dilatation operator. I can define some other choice of dilatation operator by some boost. In other words, I can talk about quantizing about the trajectory of something, some other time-like geodesic, and I get a different equivalent description. So I'm just choosing some arbitrary time-like geodesic. We'll see in a second that sitting at rho equals 0 is a particular time-like geodesic, and describing physics from the point of view of that observer. But I can choose any other observer, and I get exactly the same physics. Good. OK, so one other aspect about this basic ADS physics. You can ask, now we're in this curved spacetime, how do forces behave as a function of separation? So in other words, if I'm some observer at rho equals 0, and I have some charge, and I have some friend who has charge at some other point in the spacetime, what is the force between those two charges? Of course, in the limit that our separation is very small compared to the Ats curvature scale, I have to just get back the standard answer in flat space, because any curved manifold at sufficiently short distances just looks like flat space. But you can ask what happens at distances much larger than this Ats curvature scale R. And the answer is very simple to obtain, because we can just use Gauss's law. So say I'm at rho equals 0, and I have some friend at rho star. I want to ask, what is the geodesic distance between rho equals 0 and rho star? And then what is the surface area of a sphere, a spatial sphere, centered around rho equals 0 with radius rho star? So for this purpose, it's very convenient to translate to yet another metric. So we have the spatial part of our metric is just 1 over cosine squared rho, d rho squared plus sine squared rho d omega squared. But I can rewrite this using coordinates kappa such that d rho over cos rho is d kappa. This corresponds to cosh kappa is tan rho. And in this coordinate system, I just get d kappa squared plus sinh squared kappa d omega squared for my spatial metric. So you might ask, why didn't I just use this coordinate system from the very beginning? The only reason is that kappa has to go all the way to infinity to get out to infinity. Our rho coordinate system had the nice advantage that infinity was a finite distance away. But I mean, this is another perfectly good global coordinate system. And what it makes manifest is that if I go a geodesic distance kappa, then I suddenly have a sphere around kappa equals 0 with surface area sinh to the d minus 1 kappa star. So at very, very small kappa star small compared to 1, this is just kappa star to the d minus 1, as you'd expect. Sorry, this is proportional to. There's some factors of 2 and pi. Yeah. Sorry, yeah, you're right. Absolutely. Sorry, thank you. So at large kappa, spheres have an enormous, enormous amount of area. And that implies that the potential I see from a charge at rho or kappa equals 0 at a distance kappa falls off like sinh to the d minus 2 of kappa star. So what this means is that ADS is in some sense ultra-local. Note that this is approximately an exponentially decreasing function at large kappa star. And so forces between distant observers fall off exponentially fast. This is the force associated with some massless particle because we used Gauss's law. But generally speaking, all forces fall off exponentially at long distances in ADS. So this means that it's very hard to sort of send information to your friend, and it's very hard to affect a distant observer. And you can verify this qualitative Gauss's law analysis by actually solving the equations of motion for a free Maxwell field in ADS, and you obtain the same qualitative behavior. Yeah?
So when you say that it's exponential, it's also
Yeah, so that was why I changed coordinates from rho to kappa. In this metric, the distance between me and you is exactly just the integral of kappa. So yeah, I shouldn't have skipped that step. But yeah, the geodesic distance here is just kappa star. And so this really is, I think, the right way of thinking about it. OK. So this further sort of supports this idea of ADS as kind of like a cavity. I mean, you're not very affected by things that are very far away from you. So now let's study the geodesics in for gauge fields? Yeah. Maybe. I mean, I would have said naively no, because at short distances, it's just the usual force.
Yeah, but what about magnetic monopoles? Do they also have an exponentially falling force, or is there a string?
I don't. I mean, in the phase where the monopoles are confined?
No, I mean, if this is like, if the Higgs phase interpretation is correct, then you expect the electric forces fall off exponentially, but magnetic forces can tunnel through this because of strings, so they don't fall exponentially.
Well, I mean, I don't think I know what the answer to this question is. I mean, I think that from the point of view of ADS, if I have some local equation of motion and I don't have a negative mass scalar, all the forces fall off quickly. If from the point of view of the CFT, if we have time, we might get to deriving this formula directly from the Bootstrap, as you know extremely well. And in that case, there's no way that it doesn't fall off exponentially. But I don't know.
I guess this computation carries over like in the same way for magnetic monopoles, right?
I think so. I mean,
Yeah.
I think it. Yeah. I mean, you can dualize the electromagnetic field and say exactly the same thing. OK. So now let's find the geodesics in ADS. So one way of finding the geodesics would be to write out one of these coordinate systems, write out the geodesic equations in one of the coordinate systems I've chosen, and solve them. And you would get the answer, but it's rather laborious, and it doesn't make the symmetries of the problem manifest. So I think a nicer way to obtain the geodesics is to use the Lagrangian formalism for the purpose that I believe it was originally invented, which is to understand the motion of objects on constrained surfaces. And thus, we can view a particle moving in ADS as a particle moving in this d plus 2-dimensional space-time with this constraint imposed. So the Lagrangian for a single particle in that space with that constraint is just the action is the integral d tau along its world line of x dot plus lambda So lambda is just a Lagrange multiplier forcing us to live on this hyperboloid. And x of tau is the trajectory of our particle. So now we can derive the equation of motion for x and lambda, which is very simple. We just find that x dot dot a equals, well, it doesn't matter. Just keep this. Equals lambda xa, and then just the constraint that x squared is 1 in our metric. So now what about this Lagrange multiplier lambda? It's appearing here explicitly, but it's supposed to be able to take any value. We can rescale tau any way we like, and we'll get a rescaling of lambda by a positive number. It's a positive number because we have two derivatives, and so we'll get the rescaling factor squared. So that means that we can choose lambda equals plus or minus 1, or lambda equals 0. These correspond to null geodesics, space-like geodesics, and time-like geodesics. So let's just choose minus 1 to study. It will turn out time-like geodesics. And now we have an extremely simple equation, which is just x dot dot equals minus x. So this is an equation that we know how to solve. We can just write xa as a function of t. We can reparameterize our world line conveniently in terms of the coordinate that will turn out to be t. And we get some coefficient v cosine times cosine of t plus some coefficient v sine times sine of t. And those are our general solutions for our trajectory. Now we need to impose the constraint. The constraint just implies that v a cosine v cosine a cos squared t plus va sine v sine plus va cosine sine times sine of 2t is equal to 1. So that gives us three constraints on our parameters v. It tells us that va sine v cosine a has to be 0, and v cosine squared equals 1, and v sine squared equals 1. We need this constraint to be true for all t, so that's what's required. And so now we have all of the time-like geodesics in ADS. So there's a simplest possible solution, which is trivial, which is just x0 equals cos t, and x d plus 1 equals sine t. That solution corresponds, if you remember our coordinate identifications, our coordinate identification, recall this is supposed to be identified with cosine t over cosine rho, and this is supposed to be identified with sine t over cosine rho. So what does this correspond to? Well, it just corresponds to a particle sitting at rho equals 0 for all time. So we found one geodesic, and it just, as promised, this guy sitting at the origin. But now, there are many, many other solutions, and I just want to highlight two different examples that solve these constraints. One is x naught is cos t over cosine of some rho star. X d plus 1 is sine t over some cos rho star. And x1 is cos t tan rho star, and x2 is sine t tan rho star. So what does this correspond to? Well, we're not sitting at rho equals 0 anymore. In fact, we're sitting always at rho equals rho star. But our x1 and x2 coordinates, which parameterize, roughly speaking, the spatial section of ADS, are rotating around. So in other words, this solution corresponds to some particle at some fixed rho star that circles around an ADS with a fixed period. So there are geodesics that correspond to a free particle in ADS that are orbiting the center. This has nothing to do with any, there's no external force acting on this particle. These are just the motions given by the space-time geometry. So that's somewhat interesting. We have these circular orbits. We can also have elliptical orbits if we like. And there's another extreme, which is x naught equals cos t over cosine rho star. X d plus 1 equals sine t over, sorry, just sine t. And x1 equals tan rho star cosine t. So what does this trajectory correspond to? Well, here we're not actually at a fixed rho star. If you go back to the identification with between the x's and t and rho, instead, this trajectory corresponds to a motion where we just slosh back and forth in a particular direction. So the extreme limit of an eccentric orbit is one that just falls back and forth through the center, and that's what this other example does. So these are two different examples of time-like ADS geodesics. All the other ADS geodesics are something roughly like this, exploiting possibly moving in the other directions and orbiting with some eccentricity. Now, there's a very surprising property of these geodesics that wouldn't have been totally obvious if we had not used this embedding space formalism to derive their trajectories, which is that they all have exactly the same period. Generally speaking, when you move under a force or in some general space-time, all of the different motions with various different amplitudes and directions are not going to have exactly the same frequency. So this is a feature of ADS physics that has a very nice interpretation in conformal field theory. And in particular, we'll see it in just a second when we study the quantum mechanics of this same particle. So maybe someone can answer this question. What do you expect the energy spectrum to be given that all of the motions have the same period? Sorry? Yeah. And all equally spaced, right? So all of the energy levels have to have an equal spacing, which is just given by some number, which we could set to be spacing of 1 in some units. And that's, in fact, what we'll see when we quantize a particle in ADS. So any questions about the ADS geometry and the geodesic trajectories?
When you say all geodesics are like this, only the ones that don't get to the boundary, right?
Good. So we chose to study the time-like geodesics. So we can take the limit of an extremely boosted particle, where we take rho star for either of these all the way out to pi over 2. That would just correspond to some particle that has more and more and more energy, so it gets closer and closer and closer to the boundary. And in the limit that rho star goes to pi over 2, we would just get a null geodesic, which is just a light ray bouncing back and forth. You can never boost to space-like. So I mean, space-like geodesics are not particle trajectories. But I mean, you can study them very easily with just the plus sign for this equation, and these cosines and sines become coshes and sinches. And this also, by the way, again encodes this idea that ADS is like a box. If I have a finite energy particle, it only gets a certain distance from the center before being pushed back. So even though the space is infinite, with finite energy, I only explore a finite region. Any other questions or comments? OK. So now let's study the quantum mechanics of this free particle. So if one likes, one could write down a Lagrangian for the single particle motion and derive a Hamiltonian and derive a Schrodinger equation and try to quantize the particle that way. But instead, we can use the symmetries right from the beginning. So in particular, we have this SO2 comma D set of isometries. This is the same thing as the conformal group in D dimensions. And I'm sure you studied earlier on representations of the conformal group. So in our case, we're in exactly the right situation to monopolize on that knowledge because our Hamiltonian is the dilatation operator. And so our particle in ADS has to transform under the conformal representations in exactly the way that a primary state and its descendants transform. So in particular, the conformal algebra has the structure of raising and lowering operators, where the momentum generator raises the dilatation energy and the special conformal generator lowers the dilatation energy. And so we can talk about a primary state with the property that and it's annihilated by all of the special conformal generators. So what does this have to do with the actual quantum mechanics of a particle in ADS? Well, what we'd like to know is the wave function and the energy levels of our particle. So we'd like psi of t, rho, and omega. Just a conventional wave function for our particle as a function of time in rho and omega. The key property that really allows us to tie this representation theory to determine this wave function is to note that the isometry generators of ADS, which are identified with the conformal generators, have to act as differential operators on this wave function. So we can generate both the ground state of our particle and all of its excited states by first solving this equation And then determining all of the other excited states. So excited states are supposed to be p mu squared to the n, p mu 1 through p mu l, acting on our ground state. We can realize all of these wave functions just directly in terms of the symmetry algebra. So what does this mean concretely? Well, I told you that it would be a great exercise to work out what the conformal generators are in global coordinates based on their simple expression in terms of the hyperboloid coordinates, the embedding space coordinates. And so let me just tell you the answer for a few of the generators. So let's study ADS3. In ADS3, there are two K mu generators. We can think of them as K plus and K minus in some basis. And so K mu is I times L d plus 1 mu minus L0 mu. And explicitly, in terms of our global coordinate system, it takes the form sine rho dt plus I cosine rho d rho minus plus 1 over sine rho d theta. So this is k plus and minus. And you could just work this out based on the formula in terms of the x's and the change of coordinates. So since the conformal generators act via these differential operators on the wave function of our particle corresponding to, for example, psi naught, the primary or ground state, we just need k plus or minus equals 0. So what does that correspond to? Well, if k plus and k minus annihilate psi, then any linear combination of them is going to annihilate psi. So in particular, there's a linear combination of k plus and k minus that just acts as 1 over sine rho d theta. So this says that d theta psi is 0. And then the other linear combination is just this particular operator. So we need sine rho dt plus I cosine rho d rho acting on psi to vanish. So that just corresponds, that simple equation has the solution. Psi is equal to e to the it cosine rho raised to the delta. So if you've studied ADS-CFT before, you may recognize this as the correct wave function for a free particle in ADS with conformal dimension, corresponding conformal dimension delta. And in particular, note that d psi is just dd I d dt psi, which gives delta psi naught. So we recognize that this is, in fact, the conformal dimension because d, the dilatation operator, is just minus I dd global coordinate time t. So this immediately tells us what the ground state of our particle has to be. What about excited states? Well, there's this formula very similar to this one for p. P plus and minus sine rho dt minus I cos rho d rho plus or minus 1 over sine rho d theta. As you know, all of the excited states take this form. So we can compute the excited state wave functions explicitly by brute force by just acting this differential operator on our ground state wave function any number of times we like. So that's one way to understand the quantum mechanics of this free particle. Now, if you're very good at finding patterns in Mathematica, you could perhaps start with this state and act with p a lot of times and look at what the results are and try to guess a formula for the general state with n of these factors and L of those factors. But you don't have to. There's another way. So before I tell you that, just one other comment about this. This is e to the I delta t, cosine to the delta rho. So what does this look like as a ground state? Well, it has the behavior you would expect for something sitting at the origin. Cosine to the delta rho may seem like a function that isn't so well localized at the origin. You can see that it's maximized at rho equals 0. But note that since as you go to rho equals pi over 2, you're going infinitely far away. In terms of geodesic distance, you can rewrite this using our formula earlier. You'll see that this is some function that's falling off exponentially fast as you move away from the center of ADS. And in some approximation, this is just some Gaussian wave packet sitting at the origin. So that agrees with the physics of some geodesic that just sitting at the origin. Yeah?
If I was to do ordinary quantum mechanics, like write down some Hamiltonian, would this delta show up in the Hamiltonian? Because it seems like there's many ground states with delta.
Good. So the question is, what fixes delta? And that's what we want to get to. That's what I'll get to in a second. So if you were to write down your first quantized Hamiltonian correctly, your first quantized Lagrangian, and then you derived a Hamiltonian, and you went through all of that process, you should learn that there's a relationship between delta and the mass parameter of your particle, right? Here, the thing that's missing is I don't know what the mass of this particle is. So that's something that you can discover that way. You can also discover it very easily in a different way that I'm about to say. So right now, we don't know what sets delta. That's the only free parameter. We've also assumed that we have a scalar. We don't have any spin.
Why couldn't we have an arbitrary function?
Because I wanted d psi to be delta psi naught. I think that fixes it. OK, so what if we want to sort of figure out the properties of all of these different states, the excited and the ground state, simultaneously? Well, we might want to solve some differential equation. We might want to write down a differential equation such that all of these ground states are simultaneously a solution. What that means is that we need a differential operator that commutes with all of the conformal generators. Now, none of the conformal generators individually commute with all of the other conformal generators, but there's an object that you probably also heard about and that you might use to, say, derive conformal blocks that does. So there's a conformal Casimir, and it takes the form d squared plus 1/2 p dot k plus k dot p plus m mu nu square m mu nu in terms of the conformal algebra. Now, this is an abstract operator in the Hilbert space, but it's realized on this space of wave functions as some differential operator. It's a second order differential operator because d, p, k, and m are all first order differential operators. And you can check, or maybe you already did check, that this commutes with all the symmetry generators. So in other words, all of the wave functions have some nice eigenvalue with respect to this this operator. So from the point of view of ADS, what is this operator? Anyone? Exactly. So this is just the Laplacian in ADS. So of course, there's another way of obtaining free particles that all of you are clearly sophisticated enough to know very, very well, which is you can study a free quantum field theory. We haven't talked about quantum field theory at all so far, but if you like, you can study a free quantum field theory. And you know the equation of motion for a free quantum field theory is del squared plus m squared phi equals 0. And this is satisfied by, this is an equation that's satisfied by all of the modes of phi. So from our point of view, just building up first quantized quantum mechanics, we would naturally be led to introduce this operator and this one just to try to classify all of the wave functions. And then we could, one way to make the connection between the mass of the particle, m, and the scaling dimension delta is to solve this equation. So there's a very quick way of determining what the relationship is between m and delta. We already proved that this is the ground state. And so the ground state is an eigenfunction of del squared. And this is supposed to be our mass squared. So we can just apply del squared to this very simple function and relate that to m squared times that function. That gives us the well-known relationship between the mass and delta, which is just that m squared is delta times delta minus d. So that's one way of obtaining this relation. Now, say you want to determine all of these modes right away, and you don't want to try to guess by acting with p a lot of times the wave function. There's a much, much better way, which is just solve this equation, and you'll find that all of these modes are solutions. So that's a not particularly fun exercise in separation of variables, but of course it's straightforward. And it allows us to write down some closed form expression in any number of dimensions for these wave functions. They're just e to the minus I plus I ENL t times a spherical harmonic in angles times some function cosine to the delta rho, sine to the L rho, times a 2f1 of minus n delta plus L plus n, L plus d over 2 of sine squared rho. So this is the answer. This is the expression that you would eventually get if you acted p many times on psi naught and organized it in terms of nice things, tensors that transform nicely under angular momentum.
So J is a list of many quantum numbers?
So J is a list of many angular momentum quantum numbers. So none of this depends on J except through spherical harmonic. OK.
The mass squared here is not necessarily the mass squared in the Lagrangian flat space. It may also include a curvature coupling, right?
Sure. Yeah, I mean, I don't know how to relate the Lagrange. I mean, I don't. Is there a one-to-one mapping between Lagrangians in flat space and Lagrangians in ADS? I mean, yeah. So this is just the mass squared that appears in the ADS Lagrangian. OK. So there are many ways of thinking about quantum field theory, of course. One way of thinking about quantum field theory is as we start with some Lagrangian and we derive, we solve the equations of motion. well, we already did that. These are solutions to the equation of motion. And then we impose the canonical commutation relations. So that's one route that we can follow. But of course, the actual physics of a free quantum field theory is very, very simple. A free quantum field theory is characterized by the fact that the total energy is just a sum of the energy of all the individual particles. The particles don't talk to each other at all. And so in fact, once we've solved for the wave functions of all of the different possible modes of a free particle, we can actually immediately construct the quantum field operator in ADS. It's just some sum on NLJ of some normalizations so times a creation operator, or an annihilation operator for this mode, plus the Hermitian conjugate. So, of course, one could have started with the QFT and derived this equation of motion and gotten here, but conceptually, a free quantum field is just a field that can create and destroy any number of particle modes weighted by their wave function or the wave function conjugate. So in order to generalize, in other words, from the quantum system of one particle to the quantum field theory, we would just introduce a Fock space where there are any number of particles with any of these modes, NL and J. But there's some crucial fact here, which is how do we normalize these modes? And to correctly normalize these modes, we have to obey the canonical commutation relations. Yeah.
Maybe you already said this, but what boundary conditions did you put when you solved the Laplacian?
Good. So I impose boundary conditions such that it vanishes as I go out to the boundary. I don't want any modes that have support out at the boundary.
Does that translate to the same boundary conditions that we put to solve the control blocks or something different?
I don't know. I'm solving the Laplacian in ADS as an operator on ADS coordinates. If it's the same, well, it's the same operator as a combination of the conformal generators, the same operator, but the representation is different, right? And the conformal, when you try to compute the conformal blocks, you study a 4-point function, and you act the conformal Casimir on sort of 2 of the external operators, but they're just CFT operators, so you're just acting in the representation those CFT primaries living in D dimensions, and that's what you're doing here. You're solving just the ADS Laplacian the way that you naively would for when you study quantum field theory. How do you know? So, you can check explicitly, but the intuition that I would suggest is that the Laplacian in ADS commutes with all of the isometry generators in ADS, and the conformal Casimir commutes with all of the conformal generators, so they should have to be the same thing. But you can just check it if you like.
If you just suppose that wave functions decay, it still is not enough, right? There's still an ambiguity for a good. So well, there's an ambiguity of, you mean whether you choose delta or d minus delta? Yes, this is some other ambiguity. So you have to fix which of these 2 solutions you're studying. Yeah. Yeah.
In the surface setup, the skin of our unitary boundary is d minus 2 divided by 3y.
Sorry?
In the surface setup, the skin of we have the unitary boundary. Theta should be larger or equal to d minus 2 divided by 2.
Yes.
And then you can block the data binding, and here we get later mass curve.
So yeah. So. Oh, so I think the question was, are we allowed to have negative mass squareds in ADS? Is that what you're asking? The answer is yes. So for scalars, but not for higher spin particles, we're allowed to study negative mass squareds. You can ask, how could that possibly be stable? And the idea is that if your scalar field, which starts off at the origin, starts to try to roll, it can't just globally over the entire space start rolling at once. You need some bubble, basically, that's starting to roll coherently. And the gradient energy from the wall of that bubble is enough to sort of pull it back as long as you satisfy the unitarity bound on delta. So that's why negative mass squareds in ADS, if they're small negative mass squareds, don't lead to instabilities. If you have a very large negative mass squared, then you have a non-unitary theory. Yeah?
Is there any nice ADS interpretation of the Conjugate?
Probably, but I don't know. I couldn't tell you what it is. I mean, presumably it's some combination of derivatives that isn't the quadratic Casimir squared, but I don't know. It's a good question.
The Banach operator.
Okay.
The conformal Laplacian squared.
Okay. Good. Okay. Well, why don't we end here? We have a description of the quantum mechanics of a particle, and we now are starting to know how to build quantum field theory. And then tomorrow we'll pick back up with quantum field theory and actually study the ADS CFT dictionary as it's usually deployed, relating the bulk field phi to some CFT operator O, and then we'll start talking about perturbation theory and other subjects.